one more minute here for anyone logging in at the last minute there. Okay, with that, I think we might as well go ahead and get started here. My name is Brian Bierschbach. I'm with Keysight in Minneapolis, and I want to thank everyone for joining us today for a webinar on identifying sources of interference in the wireless environment. And I want to thank our partner, Electrorent, who is helping offer this today. And with so many wireless devices out there, to me, it's kind of amazing things work as well as they do, and sometimes they don't. And that's kind of what this webinar is all about, is going out in the field or any place for that matter and identifying sources of interference to help make sure that your devices work in all environments. So with that, everyone who's logging in should be on mute. If you can remain on mute through the end of the seminar. The seminar has about a 45-minute run time. If you do have questions, type them into the chat and we'll try to address them on the fly. But to keep things on track, if everyone could remain muted, and then at the end we'll have time for you to unmute and ask live questions. So we also have an evaluation form we're wondering if you can fill out at the end. I think that pops up automatically at the end, and that really helps us refine our seminars as time goes on. So yeah, with that, again, my name is Brian. Please chat any questions, or we'll have time at the end for live questions. And I've got Randy Tanner, who is kind of our FieldFox portable analyzer expert. He'll be going through our slide presentation, and I hope everyone finds this of use. Thanks. Go ahead, Randy.
Well, good morning, everyone. Thank you for joining us today. As we talk about sources of interference and interference in the wireless environment, I've seen a lot of things. There's a lot coming. The more that wireless equipment is out in the world, the more there is interference issues, random as well as from the networks themselves. And so we'll talk about this. This morning, I'd like to cover real briefly several different areas and then spend a lot of our time using the FieldFox, looking at some spectrum, looking at those tools and how they work. So I'm going to start with just talking about why we might want to monitor spectrum, and then what is interference, what types and sources are there, and then what kind of tools and techniques we can use, and then specifically talking about and demonstrating the FieldFox. And we'll just be using an antenna looking at some things over the air here. So let's get started. So the first thing I want to mention just briefly is why do we monitor spectrum? So the first area is just to verify the RF environment. So we're trying to deploy a network, or we're trying to build devices that are going to be wireless. What does the RF environment look like in the world where we're trying to transmit? So we're trying to make something, let's say at 900 megahertz. So we want to learn at our specific frequencies or channels, what's already out there. What does that look like? Another reason to monitor spectrum is to validate. Okay, we've put our network out, or we've got our system running. Are we getting the coverage we need? Are we using the channels we're supposed to? What does that look like? And then another reason would be to detect and mitigate interference, which is what we're going to talk about today. There's other reasons. There's monitoring spectrum like the FCC would for validating that people are working within the rules and the requirements. A lot of different reasons. So most of us that make transmitters or receivers are trying to follow the rules and make our systems work as well as they can given the circumstances of the environment. So as we talk about RF interference, let's talk a little bit about where it comes from, what some of the sources are, and what we're going to define it as. So we're going to call interference as an unwanted signal disturbance, which affects normal wireless operation or wireless devices. And I would say primarily interference is a receiver issue. It's a receiving issue. The receiver, for some reason, is not getting the transmission properly. For a variety of different reasons. I guess it could be a transmission problem, but it's more likely a receiver related problem. So let's look at some types of interference. So in really general terms, there's something called co-channel interference. From the little diagram you can see we've got our receiver, we've got the frequency that the receiver would receive, and there's another co-interferer, which would be something else transmitting on the exact same frequency. So it's stepping on our frequency, and co-channel interference may or may not cause problems. If it's really low level and and not affecting your receiver sensitivity, and your signal's really strong, your receiver's probably okay. If it's a strong interfering channel, then it could affect your reception. Or a lot of times we think of interference as, well, okay, so my system's not working because of interference. It can also be just a degradation, that your system's working, its data throughput's not what it's supposed to be, that type of thing, caused by any type of interference, but particularly co-channel. We'll talk later on in the presentation. So if we find interference, now what do we do about it? We'll address that a little bit later. Adjacent channel interference, this is where the interferer is not technically on your channel, but something about its transmission is causing a problem. And there's a brand new circumstance right now where adjacent channel interference is really a concern, and that is in the C-band. The C-band is around 3.7 to 4.2 megahertz, in that range, gigahertz. And that's traditionally been a band for satellite communications. Recently, the government sold $80-some billion worth of that spectrum to the cellular carriers. And so the cellular carriers are going to start using that spectrum. Now, they're allocated a certain part of that band, and the satellite is allocated another part of that band. But the concern right now is the satellite Earth stations are very concerned that there will be adjacent channel or out-of-band interference caused by the 5G deployment in this band. And so that would be a sample of adjacent interference. Why is it so important there? Well, Earth stations are receiving extremely small signal levels because the satellites are way out in space. And so by the time it gets there, it's a really low signal level. The 5G towers are going to be transmitting at relatively high power. So even though it's not in the band, it could be that the low level skirts that go out of band are still too high level for the satellite dishes. And so that's a concern, and that would be a concern about adjacent channel interference. Another common thing is broadband noise, and this is just the noise level of the environment is higher than you expected when you design your system, and so you don't have enough signal to noise ratio to be able to get a good signal. And this can be common in very busy spectrum. And I like to use the analogy, if you're fine dining with your friends or your spouse and you're in a restaurant and you're the only ones there, you're having this nice quaint little conversation. Well, the restaurant fills up while you're there, everybody's having their nice quick conversations. It creates so much noise that everybody has to start talking louder to hear each other. Eventually you get to the place where it's a miserable experience because it's just shouting. That's kind of an example of broadband noise in your channel that isn't any one thing, but the accumulation causes problems and interference with what you're trying to do. Some sources of interference. So one source can be internally generated. Something about your system or your network is creating problems. Something's broken or something's not working the way you expected. And so that is internally generated interference. Typically that is a network type of a problem where your whole network is interfering with itself. Another source, and what we commonly think of as interference would be some external transmitter, amplifiers, repeaters, lightning arresters, brake, all kinds of things that are creating a signal that is in your channel or adjacent channel, or just raising the noise floor. So we typically think of, I've got interference and it's somebody else's fault, and that's externally generated. And then a third common source, especially with broadband digital signals, is intermodulation. And this is where two somewhat powerful signals combine at some sort of a junction that is effectively being a diode, like a rusty bolt or something like that. There's all kinds of strange phenomena that cause this. And those two signals combining create a new signal at a different frequency. And that different frequency turns out to be co-channel or adjacent channel interference with your system. And this is a pretty common thing. As they deployed the LTE network in cellular, that became a really common problem. And so a technology called PIM testing came out to test for intermodulation defects and problems in cables and at installation sites. So those are some sources of interference. Independent of the source, we need to be able to detect it and find it and know where it is. So what kind of tools do we have to use to do interference monitoring, and especially detection, spectrum monitoring, interference detection? So primarily, people use spectrum analyzers. There's some other types of equipment, some specialized radio receivers and things like that can be used, but typically those type of devices are really only validating whether the system works or not, but it doesn't really troubleshoot if there's a problem. A spectrum analyzer is really the best tool because you can look at the spectrum and you can look for things that don't belong, and we'll see that as we run through the demos here in a minute. The other is a more modern tool is a real-time spectrum analyzer. We'll talk about the differences of those two. We'll actually use them both. They're both on the FieldFox, and see how they relate when you use one versus the other. But the real-time spectrum analyzer has been a really beneficial tool as we get into digital, wideband digital communications. And then once we're using those tools, there's a lot of techniques within those tools, a lot of sub-tools within there. So the kind of traces we can use and how those traces work and the states of those traces, we'll see some of that here in a minute. Something called a spectrogram, other people call it a waterfall display. It's the same, two terms for the same thing. We'll see that. Can you record your traces and review them later on, or record them in the middle of the night when you're not there and look at them the next day? Tune and listen. This is the ability to see if there's any kind of sound demodulating an AM or an FM signal to see if there's some clues. It's really a part of the clues in doing the interference detection. Ideally, you suspect maybe somebody's transmitter is causing the problem, and you can just turn it off and see if that goes away. That's usually not possible. People don't want to bring down their systems or their networks as they're trying to find problems. That makes it way easier, but not often capable. And then the types of antennas you're connecting to the spectrum analyzer can vary from an omnidirectional antenna to, in the lower image there is a directional antenna, Yagi antenna. So directional antennas to try to get the source of what direction the signal's coming from. So we're going to look at the FieldFox here, and the FieldFox display. I'm going to make some measurements here, but I thought I'd just, those that aren't familiar with FieldFox, just introduce it to you real briefly. This is a handheld instrument. It's about 7 pounds. And it's got a lot of design features in it that make it really useful for the field, as well as a high performance instrument. So first of all, it's got a really good backlit screen so that it's easily seen in all kinds of environments, outdoor, indoor. Backlit, large keys so that you can use it with gloves or in the dark. It was designed to be used in a rugged environment, so it doesn't have any moisture or dust can get inside it. It's got an IP53 rating on it, so it's very rugged. It's designed to be used outdoors in the rain or the snow or in whatever environment you find yourself in. And then on the top of the unit is the main RF connectors. There's 2 ports. Every FieldFox will have 2 ports on it, whether you need or use both ports or not. It's designed to have all of its functional electronics built into the base unit, and then with license keys, you can turn on those various functions as your needs change or grow. We make units that go from the lowest frequency unit will go up to 4 gigahertz, and then we make units that go all the way up to 54 gigahertz. And you can see in the top right, different connectors are used for different frequency ranges, and that's just because of the performance of different connectors. So the most common in connector is used below 18 gigahertz, and then we transition up to different connectors as we go to higher frequencies. And then on the sides of the FieldFox, on the left and right side, are different hatches or connectors, depending upon what you want to be able to do. I've actually got a FieldFox connected to my laptop using the LAN port, and we'll be showing you a screen image that's available on my laptop from connecting the FieldFox to the LAN port. Again, designed to be very rugged, very dedicated, and very functional. And we'll talk about the functions here on this next screen. So we're not going to go through the details of all these measurements. We're going to see a few of them while we do the demo, but just to get an idea of the breadth of potential of the FieldFox. So it can test cables and antennas. It's a full 2-port network analyzer with the proper license keys activated, spectrum analysis, real-time spectrum analysis, and interference analysis. We'll be doing some of that today, making power measurements, being able to scan different channels over in the center right, being able to demodulate 5G and LTE signals and get specific data about cell sites and things like that. It's got a built-in GPS receiver that's used for if you're trying to tag data to GPS to location, or if you're trying to get super precise measurements, you can set the internal frequency reference of the FieldFox to be connected to GPS, and so you get a much more accurate measurements, things like that. And then we have specialty measurements like the IQ analysis for being able to look at specific IQ data in a logging scenario, or noise figure if you do a lot of work with satellite ground stations and things and you want to measure noise figure, things like that. So touched on a few of those. All of this capability would be license key activated depending upon the FieldFox that you had. The only thing that's not license key activated on a FieldFox is its top end frequency. That has to be decided up front. So let's look at some spectrum. So I'm going to bring up a FieldFox screen image here, and so everybody should be able to see this FieldFox screen, and I've got a FieldFox sitting right next to me. And so I'm going to start in the spectrum analyzer mode, and I've just activated it. So you can see at the lower side. So first of all, the spectrum analyzer right now, it's an 18 gigahertz unit. And so it's just wide open, 0 to 18 gigahertz is the frequency span we're operating in. You can see kind of on the lower end of the spectrum, there's some activity. That activity is primarily cellular bands and Bluetooth, Wi-Fi bands. And so before I go into that though, I wanted to point out across the bottom there, you see CAT, TDR, NA, SA, real-time SA. This is how the different modes we talked about on the last screen are exhibited on the FieldFox. So there's buttons underneath these soft keys, and so you can go, if you have all the licenses activated like I do on this demo unit, you can just see there's all these different modes available to the FieldFox. So that's the way the FieldFox starts, with the different modes you've got enabled. If you buy a base cable analyzer, what we call the combo box, with no modes activated, it'll just say CAT, it'll test cables and antennas, that'll be its base function. All the rest of the stuff you turn on. We also make models that start out as spectrum analyzers if you don't need to do network analysis or cable test. But we're going to use the spectrum analyzer today, which is what we're on. And the first thing I'm going to do is home in on a narrower frequency range, specifically the 2.4 gigahertz Bluetooth Wi-Fi band, and we're going to look at some signals there. So I'm going to set my start and stop frequency, so 2.4 gigahertz, stop frequency 2.48 gigahertz. And now I'm using the spectrum analyzer to monitor the spectrum that's going on at my FieldFox. I've just got a simple antenna connected to the RF input port on the FieldFox. So we see some spectrum jumping around. I will point out that the spectrum, the display on my FieldFox is somewhat faster than what you're seeing in the presentation, just because of the internet and all of those things. So while you might look at it and go, well, that's kind of a slow spectrum analyzer, it's actually moving very fast in live with me. It just slows down over the internet. But this is a standard spectrum analyzer setup. This is a trace. We see different bursts going on here. So one of the tools that we could use to try to look more at this spectrum and characterize it a little better is we can use another trace. So I'm going to go into the trace menu, and I'm going to turn on my second trace. You can see trace number 2 is underlined. Instead of being blank, I'm going to make that max hold. So now what's happening is every time there's a new, stronger signal than before at a given frequency, it holds that new frequency. So now we're basically painting in the spectrum to be able to see what's going on in the spectrum. And so you can see that we've got a variety of things. The one big wide signal in the middle, that is painted in of the Bluetooth signaling. And then the little spikes you see surrounding it, and they're actually in the middle under it also, are Bluetooth. I mean, sorry, I said Bluetooth, I think. So the big hump in the middle is Wi-Fi channel 6. And then the little spikes on the edges, that is Bluetooth. And so you can see that we periodically see the Bluetooth, but over time, using the max hold trace, we can paint in and get a better characterization of our environment. Now, if we saw, we may at this stage see something unusual. If we saw a big signal that we didn't expect that was there, or a signal, we are in a digital spectrum right now where everything is intermittent. So if we saw a signal on this screen right now that was always there, that would be unusual, and that would get our attention. Just that on its own, that would get our attention, is seeing that signal that would be always there, and I don't see that right now. There's a lot of capability in the spectrum analyzer. There's a lot of different kind of settings, setting the resolution bandwidth, the scale and amplitude, turning on a preamp or not, which we don't need right now. If you're interested more in FieldFox, we can do separate demos for you and really go into all the details. I just want you to get a picture of what some of these spectrum tools look like and what the spectrum looks like on a spectrum analyzer. But now I want to switch over to another mode. So I'm going to go to the real-time spectrum analyzer mode, and let's see how or what or if this mode is any different than before, than what we saw with the regular spectrum analyzer. So we notice something right away. I don't have a max hold trace on. We're just seeing all the Bluetooth and the Wi-Fi spectrum here. Now you noticed before it was very random on the spectrum analyzer, and we really couldn't characterize things until we turned on the second trace and did the max hold. What we're finding here, though, is that we're seeing traces and images here that are on all the time. So for instance, I'm going to go back real quick to the spectrum analyzer. So one of the things that you see in that big center section is you see the spectrum, the yellow spectrum, kind of pop up and down in little skinny bursts, and it ultimately painted in that blue. But the reality is that's not how the Wi-Fi is working. The Wi-Fi is actually bursting on or off. And so you can see now in the center that that is there all the time, and you can see another Wi-Fi over on the left that comes and goes. But you notice how it's not little fragments. It's either all there or it's not. That's one of the powers of the real-time spectrum analyzer. So what was happening with the regular spectrum analyzer is it's sweeping through the spectrum. And so when it's one spot along the sweep, it's not somewhere else. And so if something happens in another spot, it doesn't detect that. Now it's sweeping quickly, going across, but it can miss things. And so what was happening as it swept, it was catching pieces of different Wi-Fi bursts as it was sweeping, and that made it look fragmented because it couldn't capture. The Wi-Fi burst goes so fast, it's there and gone so fast that a spectrum analyzer sweep couldn't capture the whole thing. With the Maxwell trace, we were able to capture multiple fragments over time and paint in that. With the real-time spectrum analyzer, it's actually capturing this full span of spectrum continuously all the time, and it's not missing anything. In fact, in the upper center of the display, you see something that says 100% POI, 15.4 microseconds. What POI stands for is probability of intercept, or in simple terms, what's my chance of capturing the signal? So right now, the settings on this analyzer right now, that 100% means I will 100% of the time capture a signal that comes and goes in 15.4 microseconds or slower. You can see it says minimum detectable 20 nanoseconds. So we would get some level of spectrum if the signal came and went in 20 nanoseconds, but we wouldn't fully capture or characterize the signal. But this is big. This is a big difference from the regular spectrum analyzer. So why is this? Why can't, let's just have a 18 gigahertz real-time spectrum analyzer? So let's talk about that a second, the difference between these. So there's actually been three sort of main types of spectrum analyzers. Initially, it was what was called swept-tuned, and that was the go back decades and decades and decades. The first spectrum analyzers were swept-tuned spectrum analyzers, an analog type of a system where there was a filter that was sweeping through a spectrum and capturing the information. And as the filter swept, it captured the signals. Now, what could happen is if for instance, on the left in the center, if there was a signal, but my filter was on the left and that signal came and went, I wouldn't capture that signal because the signal and the filter had to align at the same place at the same time to be able to capture it. So there's some missed signals, a lot of missed signals in that technology. So then there becomes the digital revolution where we're digital signal processing with FFT. And in that case, we are actually capturing blocks in real time, and then we are converting that using FFT into spectrum. And so that's called a snapshot FFT. There's most spectrum analyzers work that way today. That's what the FieldFox spectrum analyzer is. And so what happens there is you capture a moment in time, turn that into spectrum, but there are places where you're processing that FFT and then you're moving over, so there's still gaps. There's places where you've got the signal, but there's gaps. Then you've got the real-time spectrum analyzer, and it is fully capturing the spectrum, constantly buffering, capturing, analyzing in a way that it doesn't miss anything within reason to the POI that I mentioned before. So the benefit of that is you capture everything. The downside is you're limited in span. So what happens in the real-time spectrum analyzer is you've got your maximum span that you can do real time, your capture bandwidth. And so you can't go wider than that capture bandwidth and be real time. And so that's the limit. The limit of real time is the width of your span that you can measure. So on a FieldFox, depending upon the unit you buy and its configuration, you can get up to 120 megahertz of real time span on a FieldFox. A lot of Keysight bench analyzers can go much wider than that in real time span. But in all cases, the real-time span will be limited compared to if you're just being a regular spectrum analyzer. And then of course, with swept-tune and with the snapshot SA, like the FieldFox, you can be in any span you want within the limits of the actual spectrum analyzer. So that's why we have both. And in my view, both tools have their place and are useful. When you buy a FieldFox, the spectrum analyzer would be the thing that's required to own if you want the real time. You can't buy just the real time, you also need the base spectrum analyzer. And that makes perfect sense because you're going to need both. So let's go back to the FieldFox now and look at another tool called the spectrogram. So in the real-time analyzer, the FieldFox has three modes. It's got the density display, and which is what we're looking at right now. The density display actually it uses color to show the different power levels of energy. So you notice down here it's red. Red is because this is the noise floor, and so there's always energy in the noise, so that's red. And then the other colors are related to how much time that energy is on the screen based on the different colors. And so that's how you can see that. We also have the regular spectrum analyzer mode, where now it just looks like the regular spectrum analyzer like we saw when we were using the regular spectrum analyzers. This is what would be called the trace display. And we have the same capability here that we had on the regular spectrum analyzer, where we could put in the max hold and use a second trace to be max hold if we wanted to. Blank that out. And then the third measurement is the spectrogram. So let's look at the spectrogram here a minute. So what's happening with the spectrogram, and I'm going to put this in hold mode so we can talk about it. So the way the spectrogram works is in the horizontal, you've got frequency still. In the vertical, you've got time. The bottom is the most recent, and the top and off the top of the screen is older in time. And then the color is the power level, how strong the signal was. So red, you can kind of imagine red is the signal coming out towards your face. And so that's a strong signal. And then the little blue dots is more around the noise level. And then the little bursts that you see, those are the Bluetooths. You'll see those little teeny segments that are staggered from each other. And so when we were looking at it in spectrum mode, those little Bluetooths look like they popped up in 3 or 4s at a time, the way we were capturing and processing the data. But in the spectrogram, you can see that they actually are slightly separated in time from each other. The setup I have right now is about 5 milliseconds per vertical division. And so you can see that in 5 milliseconds, there's about 3 of those bursts happen in 5 milliseconds. So one of those Bluetooth bursts happens about every 2.5 milliseconds. And you can see the duration of those bursts are very short. They last for maybe a millisecond or maybe even a little bit less. And then where that Wi-Fi spectrum in the middle looked like it was continuous in the spectrum density mode, it's actually not continuous, it's bursting very quickly. And so you can see there's multiple bursts happening every few milliseconds. You also notice there's a big trace in the middle. So one of the capabilities that we have in making measurements is we can actually use time markers, and we can scroll along and look at our different spectrum. On. And you'll see a little purple line going up the screen, depending upon how big your screen is. And you'll see as I scroll along, I can see what was happening by each trace that we captured. So this one over on the left, there was a Bluetooth burst. And then next there was a Bluetooth burst kind of in the middle of the screen, and then a Bluetooth burst on the right, and then coming back towards the middle. And then you'll see there was a Bluetooth burst in the middle right before there was a Wi-Fi burst. So you have the ability to go through and look at the spectrogram and look at each individual trace of what was going on at that moment. So let's look at one more, let's use this tool to look at one more thing here. So detecting interference is about what doesn't belong. And so if we look at this spectrogram trace, something jumps out at me. And depending upon how familiar you are with Bluetooth and Wi-Fi, there's something that doesn't belong on this screen. And what doesn't belong is this long blue line. Everything here should be really bursty, but there's this long blue line in here which doesn't look bursty. So let's turn this back on into run mode. So you can see that blue segment comes and goes, bursting along there. Well, what I'm going to do is I'm going to adjust my time per division and get more spectrum per division. And so I'm going to increase my time per division to, let's say, 100 milliseconds per division. And then I will stop it so we can talk about it. So now you can see there's this dashed line that is repetitive dashed line. This is something that shouldn't be here. And so that is the idea of interference hunting, is what's there that shouldn't be there. Well, there's this line here that shouldn't be there. So let's try to figure out, okay, well, what frequency is that line? So let's go back into our marker. We'll go back to our time markers, and we'll scroll till we see that signal. We'll get my purple line kind of over it, and we see there's a little teeny bump there. So now I will go into my regular marker and I will scroll to that little bump and see what that frequency is. 2.414 gigahertz, you'll read in the upper right of the screen, 2.14 gigahertz. So there's something at 2.14 gigahertz that shouldn't be there. Now, is it a big deal? Is it not a big deal? It is a signal, a low-level signal that is on the spectrum of our display and in the air. And so it doesn't matter. It's really low level. It doesn't look like it would matter. Well, the Bluetooth signals that we see are from a Bluetooth device that's 2 feet from my FieldFox. If this Bluetooth device was within its spec, maybe 40 feet away, that signal would be really low, and it may be more comparable to that interfering signal. So that interfering signal would then be blocking one of the frequencies that Bluetooth could operate on. It may fall in the middle of the Wi-Fi spectrum. So while it's not in general affecting things, if you have a lot of Wi-Fi traffic, it's going to be using some of the spectrum and causing interference. So you might see data rates go down. We're looking at that signal right now at this moment in time. We don't know anything about that signal. Maybe at certain times of the day, it becomes really a strong signal. And so right now, we've had reports of problems on our Bluetooth or on our Wi-Fi, and we don't know what it is. And I'm using Bluetooth and Wi-Fi as a sample here because I know I'll always have Bluetooth and Wi-Fi no matter where I am. But in any spectrum, we could be in the cellular bands, we could be in 900 megahertz, we could be in other bands that you're working with on your transmitters and receivers. So it could be that we got a report if there's some kind of interference. And we bring our spectrum analyzer out and we don't see anything. We start using these tools and we go, hey, wait, there's this little low-level signal. Maybe that's the problem. And maybe sometime during the day that becomes a high-level signal and causing our problems. In any case, this doesn't belong, and we'd want to find out, where does this signal come from? So what do we do once we have detected a signal? So first of all, we want to find out, we need more clues. So one of the things we would do is we'd get a Yagi antenna and we'd hook it to the FieldFox, and we'd start using that spectrum analyzer, and we'd rotate our Yagi antenna around and see if the level of that signal got bigger depending upon what direction we were pointing, and it would. The Yagi antenna would detect that at some location that signal's coming from, and so we would see that signal level rise. So then we know, hey, let's go in this direction because that looks like where the signal's coming from. And we may find, hey, you know what, we pointed to one of our antennas. One of our network antennas is where it looks like the signal's coming from. So maybe we're generating that signal within our own system. So I want to use the cable antenna sweeper or the FieldFox and sweep my cables and my antennas and see if there's something going wrong in there that might be we're causing our own problem. Or maybe you have the ability to turn off your transmitter and see if that signal went away. Okay, well, I was able to turn off my transmitter, that signal did go away, so somehow I'm the cause of that signal. Or it's passive intermodulation causing that signal on my receive channel. Somehow my transmit channel is interacting with something else causing this signal on my receive channel. So internally generated, there's tools on the FieldFox to check this out. Maybe that low-level signal is a PIM. That's pretty common in some industries, especially the cellular industry. You will see that low-level signal, and it will look kind of strange, and it will be PIM generated. And so you try to then figure that out. and correct the issue. The other is that it's somebody else, it's another source. In the case of the interference signal we're seeing on this FieldFox, it is another source. I have another FieldFox that's generating this signal. That is the interference. And so if I had a Yagi, I would point to the antenna. It would end up pointing to the antenna, that source. I could go deactivate that source. Sometimes this sounds really weird, but tune and listen. So tune and listen would be tuning into that signal with AM or FM and trying to listen if there's any clues maybe. Now what can happen, it's not uncommon, is that a cellular signal is intermodulating with a radio signal, and you will demodulate and you'll hear a radio station and you go, wait a minute, a radio station at 88 megahertz is so far away from me. Why is that causing interference? Well, you know, okay, that's some kind of intermodulation happening. And you can do some math and go, well, if it's at 88 megahertz, what would it be combining with to cause my problem? And then you can see what is intermodulating with what, and that will give you other clues. Ideally, you want to eliminate the source of the problem, but you can't always do that. So in the case of Bluetooth and Wi-Fi spectrum, there's rules around it, but anybody can use that spectrum. And so if somebody else is following the rules and they're creating interference for you, but they're following the rules, you can't necessarily make them stop following the rules or deactivate their transmitter. You may have to change what you want to do in your system to deal with or eliminate that interference. So again, it's about having the tools to detect the interference and then finding that interference and then eliminating the cause of that interference. If you're in a licensed spectrum and you own the spectrum, you can tell the other person to get off your spectrum. That's the case a lot in the cellular industry. The cellular companies own the spectrum, and if somebody is running a repeater, let's say, or a jammer in their office building because they don't want their employees to use their cell phones, well, that's illegal. And they don't have the right to operate that jammer on that frequency because they don't own that spectrum. So the cellular guys will use these tools, their Yagi antenna, show up at the building, find the jammer, tell the customer to turn it off, or customer tell the interferer company to turn off their jammer. Because not only is that jammer stopping the cell phone customers within the building from using it, but that jammer is going out of the building and causing other people to have problems and disrupting things. It can also be part of what creates that general noise level that causes the whole network to get messed up. So I'd like to address any questions you have. Feel free to come off of mute. If you want to see anything particular with the FieldFox, I'll bring it up on the screen and I can make some measurements or show you around the FieldFox a little more if you'd like. And if you also feel like you want to just type in a chat question, please do that as well.
Yeah, thanks, Randy. Great presentation. Like Randy said, feel free to come off mute or chat your questions in chat. Here, we'll give it a few minutes for anyone who's interested in getting answers.
I would also encourage you to, if you have some interest or some need, you can work with our sponsor today, or with Brian or Dave Walter, or any of those folks can link you up to where we can do a more detailed dive in this format with a FieldFox in a presentation. We can talk about things virtually. You can also get access to demo units if you've got something specific that you want to try.
Yeah, along those lines, we do have plenty of evaluation units. We're happy to ship them out to your office or even your home address. It's a nice way to get accustomed to the FieldFox by using it at home to look at your own Wi-Fi and Bluetooth. And you know, if we ship a demo unit out, we don't have any expectations of an order or anything like that. We just like to get the product out there so people kind of get a feel for the capabilities for when the need arises. So, like Randy mentioned, Electrorent is our distribution partner. You can get quotes from them and purchase through them. So let's see, it looks like Jim has a question. What are the typical Bluetooth interfering sources?
For Bluetooth, primarily the issues are around Wi-Fi. It can be Bluetooth. Bluetooth is designed to be hopping, and so it's always moving. And so it would be noise level can be a big one. So if there's a lot of Wi-Fi routers around and the noise floor is coming up, and your Bluetooth is then at the fringe of its distance, that can be knocking Bluetooth off. Bad devices. So a lot of times there can be devices that are supposed to be following the rules, but they're defective or broken or something like that. And so then they start creating interfering signals. Bluetooth is pretty robust though, because it does hop. And so it becomes more of a fringe issue usually, that you're farther from, you're within the range that Bluetooth should work. And there's 30 feet, there's 100 feet, there's 300 feet, there's different specs. But when you get to the edges, and there's just too much noise for you to get the signal through because there's too many devices or too much Wi-Fi in the area. So there's not often you can do anything about it. The other thing is what I find a lot when people are designing devices to run with Bluetooth. So let's say you're a company that's made products for a long time and you've always done it wired. And now you need to transfer that technology to Bluetooth, to wireless. And somebody's clicking on their keyboard. And so you're transitioning, you buy the Bluetooth chip, you put it on the board, you follow the data sheet, and then you're not getting very good results. And there can be a lot of causes for that. Usually it has to do with the design and the antenna structure that you've put on your board or those types of things. And so you're getting it to work, you just don't have good range. And that may be an interference problem, or it may be a design problem. I hope I've tried to help answer your question a little bit.
Yeah, thanks, Randy. We're going to pop up a quick poll for everyone. And then once you exit the seminar today, you'll be presented with an evaluation form. If you could please fill that out just to give us feedback, and it helps us improve for future events. But yeah, so any other questions? Anyone can come off mute or chat a question.
So one of the things I just did was I just switched the frequencies of the FieldFox into some of the cellular bands. So what you're seeing right now is some cellular downlink. I think most of these are LTE, but there's also some 5G bands out there that we can look at. But so this is an example of some of the cellular downlink bands. And as we proliferate the world with more and more wireless, there's more and more kinds of things that we have to hunt for.
Okay, I think can't close that poll if we're all done with that.
Yeah, that sounds good.
Okay,
still time for questions, anyone? And I can't remember if I mentioned this, we'll be sending out a link to this recording to the whole session. So if you jumped in late, you'll be able to view the first part of it using that link. So. Yeah, any other questions, anyone? Okay, I think that that does it. Well, thanks so much, Randy, and thanks to ElectroRent for sponsoring us here today. And Leslie, were there any other items?
Nope, I think we're good to go. Thank you. Thank you, Randy.
Right. You're welcome. Thank you all.
Yeah, on behalf of Keysight, thanks for attending, and let us know if we can help.
Have a great day, everyone.
Thank you.
Thank you all.